Hello and welcome to Math Divulged. Today we're gonna talk about, let's see, what is it? We're gonna talk about lengths and areas, right? So lengths and areas. Yeah, let's start by, um, I'll start with a GeoGebra app. Uh, let's see. Resume recording. Okay. Cool. So today we're gonna talk about lengths and areas, and we're gonna start out with what shape? Anyone want to guess? Okay, it's not really something special. We're just gonna start out with a simple triangle. Circle, square. That's all. Those are also good guesses. Those are also good things to look at for lengths and area. But we're gonna start out with a triangle, and we're gonna start out with something that doesn't really look like it has to do with area at first. We're going to start out with a theorem about Chibians. So Chibians, it sounds like a weird name, but they're just lines through a point on the triangle and a point on the other side. So say you have a point D on BC, and AD is a Chibian. If you have a point E on CA, then BE is a Chibian. And then finally, if you have a point F on AB, then CF is a Chibian of the triangle. So these Chibians, if we draw all of them, they divide this triangle up into different regions, right? 1, 2, 3, 4, 5, 6, 7. And so a question might be to ask, well, when do they a question might be to ask, when do these Chivians meet at the same point, like right now? What property do you think holds to make them meet at the same point? So someone said median. So median, if you have medians, that's a special case. Okay, let's see, perpendicular bisectors. So are perpendicular bisectors Chibians? Perpendicular bisectors go through a point on BC, but they don't go through the opposite point A. Okay, so yeah, y'all got that. Angle bisectors, yes, angle bisectors are another case. So medians, angle bisector, medians, all three medians meet, all three angle bisectors meet, and the one property that generalizes this is, as y'all said, Chivas theorem. And yeah, some of you said altitudes as well, so altitudes also meet. So yeah, the property that generalizes this is Chavez theorem. Let's see, let me write this. So the thing with Chavez theorem is that it relates the lengths. It's a property about the lengths. The lengths have to satisfy some property so that these meet. Right? And yes, as someone pointed out, the property is that AD or AF over FB. So this length right here over this length right here times BD over DC times CE over EA, or wait, this is an F right here. Don't confuse this for E. Okay, so times CE over EA. So the thing is that this equals, what is it? It equals 1. So when this property holds, these lines meet at the same point. And when these lines meet at the same point, this property holds. So Chavez theorem is an if and only if statement. It makes these two things equivalent. It makes this property equivalent, and it makes the property that these three lines meet equivalent. So so how do we go about proving this? Any ideas? So one thing we can start out with is, okay, I see the TAs here, so I'll quickly try to add. Let's see, maybe I have to stop share screen for a while. Okay, so Naveen is going to be the TA. So if you have any questions, ask the awesome Naveen. Okay, I'm going to share screen again. Okay, yeah, and let's see, it's recording. Okay, so if you have any questions, ask Naveen, and we're gonna continue with talking about these Chibians, or Chibians, I don't know. Okay, so how do we show that this is true? So the Chavez theorem is saying that these Chibians being concurrent is the same thing as this property holding. So let's start by going from here to here. How do we show that is true? Okay, so one thing is we want to find out a property about lengths. And so far, and we start out with a property about the lines. The thing is that if we assume they are concurrent, then we have to we have to start out with the assumption that they are concurrent. And let's rename this point as F. Okay, so we start out with the assumption that these Chibians are concurrent, and we want to find some property about the lengths. And so how do we relate this property to something about the lengths? These lengths are kind of weird, actually. So you see things like BD over DC. BD over DC, this, in total, we have a total of 6 variables. So we're not going to get far by comparing lengths. So let's instead use areas. Using areas, we can talk about these relationships like BD over DC. In terms of areas, you don't have to use as many points. So what is the ratio BD over DC in terms of areas? How do we relate this to areas? Okay, so one thing is that when we look at BD, it can be the base of a triangle. So one obvious triangle that it can be the base of is ABD. Another triangle might be F1BD. So, and similarly, DC is the base of the triangle ADC, and is also the base of the triangle F1DC. So, if we look at the triangles ABD and ADC first, then we notice that ABD, this triangle right here, and ADC, they share a height. Their bases are in the ratio BD to DC. So if we consider the area of a triangle, what do we notice? Okay, so the area of a triangle is base times height divided by 2. So since the heights are equal, the ratio of the areas is just the ratio of the bases. So BD over DC, the ratio of the bases, is just the ratio of the area of the triangles. So ABD divided by the area of ADC. And then similarly, we can look at the triangles F1BD and F1DC, and we get that BD over DC is also F1. I'll actually call this G so that I don't have to say F1. Okay, so this area, okay, yeah, please don't spam Naveen. Naveen is trying really hard to answer questions, and it would be really great if y'all gave him the space to do his awesome work. Okay, so the ratio BD to DC is a ratio of bases. And so if two triangles have the same height, then the ratio of their areas is the ratio of their bases. So the ratio of the area ABD to the area of ADC is, since they have the same height, is the ratio of their bases BD to DC. And the ratio of the areas GBD to GDC is also BD over DC. GBD over GDC. Okay, so now that we have this property, how can we relate it to the other? How can we move forward on showing this is true, showing Chavez theorem? So one thing we notice is that we still have a lot of points, right? Like we still have the point D. We didn't get rid of the point D. And so if we replace all these with like ratios of these areas or these areas, we'll still have the points D, E, and F. We'll still have at least 6 points. So in order to get rid of this point D, what we can do is, as someone noticed, we can subtract the areas. So we have the area ABD and we have the area GBD, right? To get rid of this point D, we subtract the areas. So area of ABD minus area of GBD. So yeah, area ABD minus the area of GBD. And what area is that? What triangle is that? This the area of? ABD minus GBD. GBA, AGB? Yes. This is the area of triangle AGB. And then similarly, the area of triangle ADC minus GDC, ADC minus GDC is AGC. So now we totally got rid of the point D, right? And we only have the points A, G, B, and C. which is good because now we only have 4 variables to deal with. Maybe they'll play out somehow in helping us solve this, prove this equation holds. Right. So one thing about fractions is that when these two fractions are when this fraction is equal to this fraction, then when you subtract the numerators and the denominators, you get the same fraction. So like for example, I'll just do an example. You can show this rigorously on your own. Like if you have 6/8 equals 3/4, then subtracting them, you get 6 minus 3 is 3, and 8 minus 4 is 4, and it's the same fraction. So yeah, so ultimately, when you subtract these, you get the same fraction. So this fraction right here, the area of AGB over the area of AGC, is the same fraction, which is BD over DC. So we converted this BD over DC into a fraction of areas. Right? And similarly, we can work on the rest. So AF over FB turns into the area of this triangle, AGC, over the area of this triangle, GBC. So GAC over GBC times, as we said before, BD over DC is AGB over AGC. So I'll just write it with the G first to be consistent. Over GAC. And then finally CE over EA. So CE right here over EA is the area of GBC, this triangle, over GBA. Oh, I don't know why I have an equals here. So is equal to C over EA is equal to GBC over GAB. And what is this equal to? Well, the GAB cancels here, and then the GACs cancel, and then the area of GBC also cancels. So we're ultimately left with 1. The areas cancel, and it equals 1. So this, the product of these ratios is equal to the product of these ratios of areas, which is equal to 1. So that's really like something really powerful about areas, is that you can get rid of using certain points when you use areas. Okay. Let's see. So what's one? So yeah. So we start. So now what we've just shown is the part where we go from the from the triangle itself to this equation. So we've shown that if the Chibians are concurrent, then this holds. But how do we go from this to the Chibians being concurrent? Right, so let's make a new triangle, and this time let's not assume that the Chibians are concurrent. Okay. Let's make a new triangle, ABC, and let's draw in some Chibians, AD, BE. But when we draw in CF, we can't assume that they're concurrent, because now we're starting with the assumption that that BD over DC times CE over EA times AF over FB equals 1. So, well, how can we show that they are concurrent? Because we know that if three Chibians are concurrent, and let's call the third Chibian AG, so or call this G, and let's call this F prime. Oh, wrong one. Okay, so this one, let's rename it as G. So we're assuming that AD, BE, and C, F prime are concurrent. We can assume that without saying anything about F, right? All we know about F is that this holds. But since we know that AD, BE, and C, F prime are concurrent, then we know that then by Chavez theorem, by the part we already proved just prior, we have BD over DC times CE over EA. And since we're applying it to AD, BE, and CF prime this time, we have times AF prime over F prime B. That product equals 1. So it turns out the F and F prime satisfy really similar equations. So if we called this blob like a blob, then we get that AF over F prime times this blob is equal to 1, and AF prime time over F prime B times the same blob is equal to 1. So ultimately, AF over FB is equal to AF prime over F prime B. So the ratios of AF over FB and AF prime over F prime B are the same. And we know that F prime lies on this segment. So ultimately, what's the point? How many points satisfy, how many points have the same ratio of AF over FB? So, right, so we said that, so basically this is going the other way for Chavez theorem. We started with, this time we started with the assumption that Chavez property is true. This property is true. And then we said, well, like, how does this F compared to the F prime for which AD, BE, and CF prime are concurrent? So if they are concurrent, then we have the same property. And so ultimately we found that the ratios are equal. So it ends up that F prime is the same point. So F equals F prime. So since F prime satisfies the property that AD, BE, and CF prime are concurrent, so F also satisfies that property. So that's why if we have Chavez property, then we have that the Chibians are concurrent. So we successfully proved the if and only if. You can, it might have been a little hand wavy. You can go back and try this yourself. Okay, and now Now, what is an example of something that we can use? What is an example of somewhere we can use Chavez theorem? Any ideas? So Chavez theorem is saying, so one way of Chavez theorem is to go from the Chibians being congruent to, or the Chibians being concurrent to the property about the ratios of the lengths. But oftentimes we don't necessarily want to find out something about length. So we go the other way around. We have the length property and we want to show that the Chibians are concurrent. So what Chibians do we want to show are concurrent? Tell me some ideas you have for D, E, and F. Ratios of lengths. So any ideas for D, E, and F? If not, I'll just give one, which is the midpoints. So let D be the midpoint of BC, E be the midpoint of CA, and F be the midpoint of AB. So it turns out, so if we draw the medians, AD, so this is not just any Chibian. Because D is the midpoint of BC, we call this a median. So this special Chibian is called a median. And then so we can also draw the median BE. And so if we draw the median CF, what do you think is going to happen? Any ideas? Okay, so if we draw CF, it turns out that they're concurrent. Why is that? So they're concurrent because of Chavez theorem. Yeah, so because all the ratios are 1. Yeah, that's right. So the if we do Chavez theorem, BD over DC times all that stuff. Well, BD over DC. Notice that D is the midpoint of BC. So BD is equal to DC. So this is just 1. So it's 1 times 1 times 1. And all that multiplied equals 1. So we have that they're concurrent. What other Chibians are there that we can try? What other points do you want to try for D, E, and F? Okay, so if no, altitudes. Okay, so let's see, perpendicular line. Someone's mentioned altitude, so we can try altitudes. AD, D being here, BE, E being here, and here. Okay, so with altitudes, how do we prove that altitudes are concurrent? Do we have Chavez property? D, E, and F. So what is BD over DC? And then if we have this ratio, then we can generalize it to C over EA, AF over FB. And then hopefully prove that this is 1, which will prove that AD, BE, and CF are concurrent. Any ideas? What is BD over DC? Like cricket's chirping. So yeah, this is actually hard. I don't know how to do this immediately. So, well, BD over DC, is it 1/3? You said. Well, what if we move A over here? then it's not 1/3. So good guess, but yeah, we don't know because we want to describe BD over DC in terms of, good guess though. We want to describe BD over DC in terms of something with regards to the rest of the triangle. And it's really hard to do that because when you're talking about these perpendicular lines, these altitudes, assign concurrent point as G. And yeah, so I think that's making an assumption. I'm not completely sure, but one idea, yeah, I think that's making an assumption. Thanks for sharing though. Yeah, so BD over DC, and someone said use trig. Yes, so if we want to use Chavez theorem for this, we're not going to be able to relate BD over DC easily to any of the other lengths. So unfortunately, if we want to use Chavez theorem to prove that these altitudes are concurrent, then yes, we have to use like one more straightforward way is to use trig. Of course, you can show that they're concurrent by doing other manipulations, other pure geometrical manipulations. But if we want to use Chavez theorem to show they're concurrent, then we want to find a trig form of Chavez theorem. Okay. So before that, though, I want to start with something that's not altitudes. So after we talk about this property, then we'll get into the trig part. Get into use the trig form of Chavez theorem. Okay, so one type of Chibian that is not the perpendicular lines and is not the median is the angle bisector. Okay, so if we have the angle bisector of BAC, of CBA, and BCA. So if we notice here, all the angle bisectors are concurrent. So why is that? It's this one we can actually use Chavez theorem. We can actually find BD over DC and the rest of them similarly. So how do we find these? Okay, let's focus on BD over DC for now. We have triangle ABC, and then we have the angle bisector. We have the angle bisector AD, so that because it's an angle bisector, it bisects angle BAC. So this angle right here is equal to this angle right here. And we can find the area or the ratio of BD over DC in a clever way. So yeah, so someone shared the answer. So BD over DC, this is described by the angle bisector theorem. And the angle bisector theorem, to show what it is, and if you haven't heard of it, it's pretty cool to first think about it for a bit. What do you think it might be? And how do we go about finding other lengths in terms of the triangle that are easier to describe than BD over DC? So when we have ratios of lengths, we saw with proving Chavez theorem that we went to areas. But right here, we only have 3 triangles, ABC, ABD, and ADC. We're not going to get many places by using the area ratios of areas. So another thing that's related to the ratios of lengths is similar triangles. So we're going to create a similar two similar triangles that have BD and DC. So DC, what triangle is this part of? So DC is part of the triangle ADC. So we're going to create a triangle that's similar to ADC that contains BD. How do we find that other point? So if we want a property about the lengths. So in order to define it, we use a property about the angles. Okay, so we want this angle to be equal to the angle BD something, and we want this angle to be equal to the opposite angle. And to do that, we create a parallel line. So if we create this parallel line, then DC is part of ADC, and BD is part of this triangle right here. BDE is similar to what triangle? CDA. So now we can relate BD over DC in terms of other lengths. Because triangle ADC is similar to triangle EDB. Okay, so what lengths can we relate BD over DC to? So one ratio is BD over DC equals ED over DA equals ED over DA. But then it involves this DA thing right here and DE thing right here. Let's see if we can get a ratio that's easier to work with. So another ratio that is also equal to BD over DC because of the similarity is BE over AC. BE over AC. Now, out of BE and AC, which length do you think is the weirder one? Is the one we want to sort of manipulate? Right, I see people saying BE. Yes, BE is the one we want to manipulate. AC, we can relate it to a bunch of other things. But BE, we want to manipulate. And this is where we remember that we're not just dealing with any Chibian again. We're dealing with the angle bisector. So with this being with AD being an angle bisector, we have ABD equals, or BAD, angle BAD equals angle DAC. We have this. And then when we constructed E, we constructed BE to be parallel to AC in order to create the similar triangles BDE and CDA. Because they're similar, or rather because AC is parallel to BE, so we have that this angle right here is equal to this angle right here. So now what do you notice? From the equal angles, you know that this is equal to this, and then this by parallel lines is equal to this. So then you notice that this angle is equal to this angle. BAE is equal to BEA. So BAE is an isosceles triangle. If you notice this length right here, BA, and this length right here, BE, they look equal. And it doesn't matter where we move A. Like if we move A up, BA and BE all increase. And if we move A down, it still looks isosceles. Right? So BA and BE are the same. And that's because of how we defined everything here. So we defined AD to be an angle bisector, so this angle equals this angle, and then BE is parallel to AC, so this angle equals this angle. So then this angle equals this angle, and BAE is isosceles. So BA equals BE. So now we can replace BE in this expression with AB. BE equals AB. So we have that BD over DC ultimately ends up AB over AC. So in this case, we didn't use areas, but we used similar triangles. Right? And yeah, we created similar triangles to show that BD over DC is equal to AB over AC. So now if we want to show that all the angle bisectors, if we want to show that all the angle bisectors are concurrent, how do we do that? Right, let's reconstruct the angle bisectors. Okay, so now if we construct the angle bisector AD, we have, as before, we have BD over DC equals AB over AC. So this length right here over this length right here. Okay. So we have BD over DC equals AB over AC. And this is called the angle bisector theorem. And with this property, we can use Chavez theorem to show that since BD over DC times CE over EA, I'm just going to assume they're defined similarly, and then times AF over FB, this equals, as we saw here, BD over DC is just AB over AC, and then CE over EA is just BC over BA, and then let's see, AF over FB is equal to CA over CB. CA over CB. So then what does this turn out to be? AB cancels out, AC cancels out, and BC cancels out. So this is 1. So the Chavez property holds for this these as well. And so it turns out that AD, B, and CF are concurrent. Of course, this isn't the only way you can prove that angle bisectors is concurrent. But it's a cool illustration of how you can use Chavez theorem. But as someone mentioned earlier, Chavez theorem isn't that convenient if we want to show that the altitudes are concurrent. The perpendicular line from A to BC, from B to CA, and from C to AB. The perpendicular lines, the altitudes. It's harder to show that those are concurrent because we don't have set ratios for the lengths. If we want to find out the lengths, we have to use Pythagorean theorem. And that's just a hassle. And someone suggested earlier that we use a special tool, trig. So we're going to convert Chavez theorem into a trig form. To do that, we use something called the law of sines. Okay, and so to find the law of sines, we're actually going to use the circumcircle. That that might be a little bit of a spoiler, but hope everything is going to turn out well. Yeah, so the law of sines is something about ratios such as A over sine A, or sine alpha in this case. So we're going to label the lengths by taking the side opposite of the letter. So for example, the side with length A would be this side. Because this side, or to choose between this side or this side, is a little arbitrary. They're both sides containing A. So we choose the side opposite A to be named A, little a, and then the side opposite B to be named B, and the side opposite C to be named C. And then alpha, we'll say this is alpha, and then this is beta, and this is gamma. So law of sines is something, also just to gain a sense of who here doesn't know trig. Does anyone here not know trig? If you don't know trig, please say in the chat. Oh wait, cool. That's totally cool. I didn't use trig much in math competitions when I was your age, so I'll do a quick intro. So the thing is, we want to relate. The thing is, when we talk about perpendiculars, when we talk about altitudes being concurrent, we want to change. Wait, please stop raising your hand. You can send me one message to say what you mean. Yeah, okay. So when we want to formulate a form of Chavez theorem that will make it easier to prove that the altitudes are concurrent, we need to relate the lengths to the angles. And so one way to relate lengths to angles is through trig. So say we have an angle like that, DEF. So DEF, this angle. Then there's then the angle DEF is related to lengths how? Like D, you can move it anywhere along the line. F, you can move it anywhere along the line. So we want to we don't want to relate it to any one particular length. We want to relate it to a ratio, something that's fixed by the angle itself. So something that is fixed is if you draw a perpendicular containing D, then and you let it intersect EF at G, then you have that this length right here divided by this length is constant no matter where you move D along this line. And so yeah, it's actually D is supposed to be fixed, but or this line is supposed to be fixed, but hopefully you get the same point. So this ratio is fixed when you have the angle being fixed. So we call this like the opposite divided by the hypotenuse of this right triangle, because this is a perpendicular, so this is a right angle. So this opposite divided by hypotenuse is the sine. Sine equals opposite divided by hypotenuse. And then similarly, if you have the adjacent, so opposite and hypotenuse, if you have the adjacent, then cosine is also fixed. Cosine is just the adjacent divided by the hypotenuse. And so we see that like this is a fraction and this is a fraction. if we want to get rid of the fractions, then we set the hypotenuse to be 1. So when we set the hypotenuse to be 1, that points us to something that we use pretty often in some circumstances, I guess, which is the unit circle. So if we have a circle with radius 1, and I'm not sure about the scale on GeoGebra, but let's just assume this let's just assume this has radius 1. Okay. Then the sine of an angle like KHI, so this angle right here, the sine of that, since the hypotenuse is just 1, since this is just 1, it's just the opposite. So it's just this length when we draw the perpendicular from K to HI, so, or from K to the x-axis. So say this is L, so KL over KH is the sine. So if this radius is 1, then the sine is just here and the cosine is just here. So yeah, so we see that, and you can read more on trig later on. Hopefully this is a sufficient introduction for what we're going to be working on today. But basically, we want to use trig to relate lengths with angles so that we can create a form of Chavez theorem that is more suitable to proving stuff like that the altitudes are concurrent. Right, so I'll just recreate ABC. And then the center of the circle is here. Okay, so the center of the circle containing ABC is here. And so let's just remind ourselves of the law of sines. So we want to say some property about A over sine alpha. And recall again that we call this A, we call this side B, and we call this side C. And then this is alpha, this is beta, and this is gamma. So we have A right here, and then we have sine alpha, and alpha is all the way over here on the opposite of A. And then to confuse it even more, sine has to do with, or we define sine in terms of right triangles. Where's the right triangle here? Well, we can create one. Yeah, so we want to create a right triangle that has this angle alpha right here, but that also has this side A right here, so that we can find this ratio. Now, how do we create that? Any ideas? Okay, so to retain this angle alpha, we're going to use a property of circles, of actually cyclic quadrilaterals. So you may or may not recall from last time, but if we have any random points E on this circle, on this side of the arc BC, then, and if we create the angle BEC, It turns out wherever E is, angle BEC is always going to be alpha. Yes, same angle. Yeah, so angle BEC is always going to be alpha. This is this is a property of cyclic quadrilaterals that since A, B, C, E are cyclic, angle A is equal to angle E. And so how do we move this E around so that we create a right triangle? Because sine has to do with, we define sine in terms of right triangles. How do we create a right triangle that that also contains this side length A? Well, do we see any right angles here? Not really, until we go here. Here we find a right angle, right? Anyone notice what the right angle is? Diameter of circle is the hypotenuse. Yes. C is the right angle. So BCE, angle BCE is right, is a right angle. So then we can transfer alpha over here. Angle BEC is alpha. Angle BCE is right. So sine, we know by definition that sine of alpha is the opposite over hypotenuse. Opposite over hypotenuse. So the opposite here is A. And the hypotenuse is BE, is the diameter. And the diameter is just 2 times the radius. So if we call the radius big R, so then the diameter is just 2R. So so A over sine alpha equals A over 2R. And what does this turn out to be? $2R. Yes. Turns out to be 2R. So similarly, what do we have for the other sides and angles? So A over sine alpha, B over sine beta. So we have A over sine alpha equals B over sine beta equals C over sine gamma, all equal 2R. This is the law of sines. And so we can use this to create a simpler form, or not exactly a simpler form, but a trigonometric form of Chavez theorem. Let's see, A, B, C. So the original Chavez theorem involved, we draw Chibians AD, BE, and just to make it concurrent, CG, we had that BD over DC times CE over EA times AG over GB is 1. So now how do we change that to, now that we have the law of sines, how can we change that into something regarding angles? So we can focus on one part of Chavez theorem, BD over DC. Right? BD over DC. To use Chavez theorem, we have to start with a triangle, right? What triangle contains BD? Well, we have ABD. We also have FBD, but we're just going to use ABD for now. Right, so in the triangle ABD, what does the law of sines say? The law of sines says that BD over sine bad, so BD over sine this angle right here is equal to, let's see, and if you have a question, you can send it to chat, and you can also ask Naveen. Yeah, so by the law of sines, we have BD over sine bad is equal to AB over sine BDA, and it's also equal to AD over sine ABD. And so to make it quicker, we're just going to say, like, right, out of these, which part of the law of sines do you want to use? Well, it turns out, like, angle B, we can't easily relate it to the other angles, like the angle that involves DC. It turns out when we say that BD over sine bad is equal to AB over sine bada, so AB over sine D, it turns out that we can, the analogous thing for talking about DC involves, yeah, angle BDA. This is BDA. I wrote it probably pretty bad. So if we write something like this for involving DC, then we get two angles that add up to 180 because they're next to each other. Right? So similarly, we have DC over sine DAC equals AC over sine angle ADC. And so when we look at this ratio again, BD is equal to this thing right here times sine BAD. Right? Sine angle BAD times AB over sine angle, I'll just call it angle D for now. Because, right, and to relate these two, we notice that angle BDA is 180 minus angle ADC. It turns out with sine that when two angles add up to 180 degrees, the sines are equal. So it doesn't matter if you're talking about this angle right here or this angle right here, the sines are equal. So we can just call it sine D, sine angle D. Right, and then for DC, we can replace that with sine angle DAC times AC over sine angle D again. So this sine angle D cancels out. And then we have just AB over AC and then sine BAD over sine DAC. And it turns out when we write the full Chavez theorem, these AB over ACs also cancel out because you have AB in the denominator somewhere else, AC in the numerator somewhere else. And we're left with sine angle BAD over sine angle DAC times sine angle ADE over sine angle EBC, and so on. Only one more fraction, but there's not enough room, is equal to 1. So this is the trigonometric form of the law of sines. And if we look back at the reason why did we make this trigonometric form of the this is the trigonometric form of Chavez theorem. Now, if we look back at why we made the trigonometric form of Chavez theorem, it's because we for the altitudes, to show that the altitudes are concurrent, we wanted to work with angles, not lengths, because lengths get messy. We have to use the Pythagorean theorem and all that. So now let's look back at the altitudes, and actually first we can look at the angle bisectors, because the angle bisectors are defined using angles. We actually don't need to use the angle bisector theorem in order to use the trigonometric form of Chavez theorem. Right, so D, E, and making F. Here's D, here's E, and here's F. So the trigonometric form of Chavez theorem is that if sine angle BAD over sine angle DAC times all that stuff is equal to 1, then they're concurrent. Well, so what is this ratio of sines? Well, the thing with, yeah, so what is this ratio actually? Sine angle BAD over sine of angle DAC. Any guesses? So how did we define D? We define D so that AD is an angle bisector. So that means the angle BAD is actually the same as the angle DAC. So this angle right here is just angle BAD, same thing. And then sine of angle BAD over sine of angle BAD, well, they're the same thing again. They're just 1. Okay, so pretty straightforward for angle bisectors. A lot easier than using the length form of Chavez theorem and then having to prove the angle bisector theorem. A lot more straightforward, I guess, than having to prove the angle bisector theorem separately and doing that. Although some of you might prefer not using trig, which is totally cool. Sometimes you just want to see the pure lengths and areas way of doing things. Okay, and yeah, and so now we're going to do what we were always meant to do, which is to show that the altitudes are concurrent using the trig form of Chavez theorem. So altitude AD from A to BC, altitude BE, and altitude CF. And why are AD, BE, and CF concurrent? Why do they intersect at the same point? Right? So we now use the trigonometric form of Chavez theorem, which requires ratios such as sine of angle BAD over sine of angle DAC. So this times a bunch of the rest is supposed to equal 1. If it equals 1, then we're done. They're concurrent. Okay, so angle BAD, what is this? We have that this is alpha, this is beta, and this is gamma. Right, angle A is alpha, angle B is beta, and angle C is gamma. So angle BAD, how does this relate to alpha, beta, or gamma? Well, this involves D, and D is a perpendicular. Yes. So because it's a perpendicular, its angle BAD is 90 minus beta. So this, or rather this angle right here, is 90 minus beta. And then this angle right here, angle DAC, is 90 minus gamma. So then we get a bunch of sine 90 minus beta over sine 90 minus gamma, and a lot of sine 90 minus something that it ends up, this cancels out with something here, and this cancels out with something here, and you end up getting 1. So yes, the altitudes are concurrent, and you can use Chavez theorem. the trigonometric form to show that. Yeah, so I think for now we'll, because it's 2:16, we'll close here. So today we used Chavez theorem, which had a lot to do with, which is a theorem with a property about lengths. And we used areas to relate. We used areas to relate the different lengths, kind of to make them more compatible and sort of solve the property. And then we went on to the angle, and we used Chavez theorem to show that the medians are concurrent at this at what is called the centroid, and then so the Chavez theorem being a theorem about like Chibians being concurrent, we also tried to show that the angle bisectors are concurrent. And to do that, we first showed the angle bisector theorem, and then we used that and combined it with with Chavez theorem to show that they're concurrent at the incenter. Well, that's not the only way to show that the angle bisectors are concurrent. We also came up with, we also briefly introduced trig and introduced the law of sines to show a trigonometric form of Chavez theorem. That made it a lot easier to show that the angle bisectors are concurrent, and also that the altitudes are concurrent at what is called the orthocenter. So yeah, this so yeah, hope you all enjoyed. Sorry that went probably quite a bit over time, but hope you all enjoyed and learned a bit about Chavez theorem, concurrence, trig, and see you next time.